as landfill regulations got more restrictive, it became much more economically feasible to recycle these industrial sludges onto land rather than put them in landfill. There are a lot of benefits of waste amendments or organic amendments. We've obviously got the main nutrients, nitrogen, phosphorus, potassium. But then you have a lot of secondary and trace elements as well. You can get some calcium, magnesium, and so on, depending on what nutrient source it is. And then, of course, as we talked about, one of the first questions in the first talk was why would you want to increase organic matter? These waste amendments can increase organic matter. It's good for soil physical properties, good for the structure. It's got good for their chemical properties. Soil organic matter has very high cation exchange capacities. It's good for water holding capacity, and there's something about biology that plants just love. Plants love organic matter. It makes the roots happy and makes the plants healthy. And depending on the source, you can also have some liming effect. Some biosolids are lime treated to kill the bugs in them, and poultry litter has a pH of about 8, so it's got some liming capacity too. Organic amendments in water quality. As we talked about earlier, organic material is broken down by microbes to release the nitrogen. So whereas chemical nitrogen fertilizer are fairly fast release, organic amendments are fairly slow release, as it takes moisture, temperature, and microbes to break it down. There can be some issues with nitrogen to phosphorus imbalance, as we generally talk to. A lot of the air, most of the air we're breathing is nitrogen, so a lot of nitrogen is lost to the atmosphere from organic sources, and therefore they don't have enough nitrogen and end up with too much phosphorus relative to the nitrogen. They can increase soil infiltration. When you do a surface application of manure, it can form these little micro dams that hold the water back, rainwater back for a little bit and give it a greater time on the surface to infiltrate. And organic matter as a whole in the soil is going to increase your water holding capacity. So therefore, when it does rain, your soil has a greater capacity to hold that rainwater and makes it more drought resilient. Other characteristics of manure, obviously you've got the urea, which breaks down fairly quickly. It's similar to urea fertilizer. And then you have the organic compounds that break down more slowly by microbes, first to ammonium and then to the plant available nitrate. Phosphorus, it's got organic compounds. In the nutrient management regulations, it's assumed that 100% of the phosphorus in organic sources is going to be plant available. And over time, that's true. It may take a little bit longer for it to be released, but over time of a year or so, it's going to be just as plant available as chemical fertilizer. Some other characteristics of manure, potassium, obviously a primary nutrient. It's very soluble. It's got secondary nutrients such as calcium, magnesium, and sulfur. Sulfur, we're seeing more deficiencies these days since the Clean Air Act. The Clean Air Act forced power plants to scrub the sulfur gas to prevent acid rain. So acid rain had a lot of sulfate in it, and that acid rain doesn't occur anymore. So we're starting to see more sulfur deficiencies, especially on sandy soils on the coastal plain. And then you also get a bunch of trace elements. Poultry litter has quite a lot of zinc. I was talking to a peanut farmer recently, and they were saying peanuts are very zinc sensitive, so on peanuts, so they can't apply more than about 1 ton per acre. That's something that doesn't affect other crops such as corn and soybeans. But there are certainly plenty of trace micronutrients in manures as well. And the nitrogen losses, we've talked about how nitrogen can be lost to the atmosphere, but the percentage of nitrogen that's lost depends on how the manure is treated. If you scrape it daily and haul it and land apply it, you can lose 15 to 35%. If you have an open lot where that manure stays around for a while, it can be 40 to 60%. And on the bottom one on the lagoons, where a lagoon is going to, the manure is going to stay in there for several months, you can lose 70 to 80% of the nitrogen that was originally in that manure before you get it back onto land for plant uptake. So substantial amounts. You don't need to remember these percentages exactly, but the main point is the longer the manure stays around before it's land applied, the more nitrogen you're going to lose. and it can be a substantial amount of the nitrogen in that original fresh manure. So in Virginia, DCR pays for manure sampling and testing. I think it's one or two, Stephanie, one or two samples per farm, but then they can take averages of all the samples that they collect. There is quite a bit of variability, but these are the average. At the top left here, beside sources, says TKN. That stands for total Kjeldahl nitrogen. The Kjeldahl is the method we use to measure nitrogen in manures. It's actually very hard to measure nitrogen because there's so much nitrogen in the atmosphere. So the Kjeldahl method is a way to measure it without getting contamination from any air. So dairy manure, it's got total nitrogen of about 19 pounds per 1,000 gallons. Swine has less, depending on the mechanism of storage. And phosphate, you can see these it's got total, it's got ammonium. Generally you take away ammonium from the total to find out how much organic nitrogen is there. And we're going to go through after this presentation some calculations about how you calculate plant available nitrogen from these organic sources. When you buy a bag of chemical fertilizer, it may say, if you buy a bag of 10-10-10, it's 10% nitrogen. All of that nitrogen is plant available. So 10% of that bag by weight is plant available nitrogen. With organics, because it takes microbes to break it down and some of the nitrogen goes to the atmosphere during that breakdown, some goes into the microbes. Not all of this total nitrogen is going to be plant available. So we'll go through a calculation of that in the next presentation. But look at the moisture percentage. This is why dairy and swine manure aren't transported much. In the right-hand column there, you can see dairy on average is about 95% water, and swine manure is even higher than that. So you're only taking 1 to 5% of that as solid material if you transport it. So it's very expensive to transport relative to poultry litter. Some nutrient contents of solid manures. Dairy and beef, you look at the TKN, the total nitrogen. Dairy and beef are 15 or 18 pounds per ton. Turkey layer broiler, they're substantially higher, 48 to 65 pounds of total nitrogen per ton. And this is because of the diet. Dairy and beef eat forage, so mostly corn and grass, corn silage and grass. Turkey layer broiler, they eat corn soybean meal. So the feed for turkeys, layers, broilers is much more nutrient dense than what cattle eat. Again, you can see the averages for ammonium, for phosphate, and these are averages across the state. But in nutrient management, you're required to have an actual test of the manure that you're going to apply, because there is a lot of variability between farms. And this is an example of the variability you see in poultry. Here we have what it looks like after one flock of chickens. So meat chickens, broilers or turkeys, they both are grown on a bed of on bedding. So a farmer will put in maybe 6 inches of wood chips, and then they'll have a flock of poultry on top of that. And this is what it looks like after you've taken the chickens out. You have this, it's called cake or crust on the surface, and it's a lot more nutrient dense than the general wood chips that are great at a greater depth. So when this is from a research pen, so when we dig it out, you can see at the bottom, it's mostly the crust, which is mostly manure with a little bit of bedding, and this forms mainly around the where the water and feeders are, and then the rest of it, the other 90%, is mainly wood chips or whatever the bedding material is, with a small amount of manure. So obviously, if a farmer is just removing the cake, it's going to be very nutrient dense. But then once in a while, he'll do a whole house clean out because the bedding deteriorates with time. The more flocks that are on there, the more it breaks down. So if you're getting a whole house clean out, you won't have as much in the way of nutrient concentration as if you just have the cake. So very important to have a nutrient analysis for the manure that you're going to land apply. Some characteristics of biosolids. Again, this is human waste that comes from sewage treatment works. You've got the nitrogen, both in inorganic and organic forms, and you've got the phosphorus. A lot of times sewage treatment plants have discharge limits. They digest to get rid of the nitrogen and blow it into the atmosphere, whereas phosphorus, there's no atmospheric form of phosphorus, so they add something like iron oxides, and that so the iron reacts with the phosphorus and then it ends up in the biosolids. And they can meet their discharge limit for water going into the local streams. Some other characteristics, potassium tends to be very low in biosolids relative to manures. There's a lot of water involved. Just think about what it's like when you flush a toilet. There's a lot of water involved. So potassium is very water soluble, and there are no discharge limits for it going into rivers and streams because it doesn't cause any harm. So the sewage treatment plants, they digest to try and decrease the nitrogen, and any nitrogen left in there is fairly stable in the organic material. A lot of times they'll add something like iron ferric chloride to try and strip the phosphorus out of the water and get it into the solids, and the potassium stays in the water and doesn't end up in the biosolids themselves. Biosolids also have secondary nutrients, calcium, magnesium, sulfur. Sometimes they have calcium carbonate equivalency. To kill the bugs and permit land application, there are several different options, and one of them is raising the pH to 12 for a certain period of time with lime. So if it's lime stabilized biosolids, it's going to have high pH and it will have a lime value. And then of course you've got a lot of trace elements. Heavy metals used to be a big deal in biosolids, but they're not nearly as big an issue these days as when the regulations first came along in the 1970s. When I was trained back in the 1980s and 90s, we flushed a lot of our chemicals from the lab straight down the drain, and now we collect all of that and it goes in hazmat containers for special treatment. So what's coming into the sewage treatment plants doesn't have those toxic elements the way it did in the 70s and 80s. Some average biosolids composition. It depends on the stabilization. So along the top row, you've got aerobic digestion, anaerobic digestion, alkaline stabilization. Each sewage treatment plant is a little bit different, and that'll affect the composition of the biosolids. So again, if you're going to do a biosolids application, you're going to need to have an analysis for what you're going to land apply. So elemental content of other sludges, again, these are kind of hit or miss. You never know what you're going to find. Most of what we land apply is animal manure. In Virginia, you do find some biosolids as well. And then very small quantities of these. You just never know. But again, you need to know, you need to have an analysis of what you're going to land apply. I think one of the most interesting ones I find, you see paper mill there. One time I went out and I saw stripes of red, white and blue being land applied, and it was paper waste from paper production, and I guess they'd been making colored paper, so that came out in the paper sludge that they were land applying. Calculating application rates. Just as for manures, as we talked about in the N&P presentation, you can do a nitrogen based. It supplies enough plant available nitrogen for a crop to be grown, but it'll over apply phosphorus. Or you can do phosphorus based application, which is based on your soil test and how much the crop needs, and you generally under apply nitrogen if you do a P based application. And then in some situations it'll be lime based if it's a lime stabilized biosolids, as I just mentioned. And if it's a lime-based application, you don't want to get the soil pH much above 6.5. Factors influencing plant available nitrogen. Obviously, the inorganic nitrogen availability is based on how much ammonia volatilization there is. And we'll come on to do a calculation where we calculate how much of the ammonia in the manure. So you've got a manure analysis. It'll tell you how much ammonia is in the manure. But then depending on how you manage it, some will go into the atmosphere. So we need to calculate that. And then organic nitrogen is based on mineralization rate and the C to carbon to nitrogen ratio. In our nutrient management regulations, carbon to nitrogen ratio isn't in there because for most intents and purposes in what we deal with, it's not an issue with manures. The only time you would have a problem with that is something like paper waste, where you would have more excess carbon And when the bugs are breaking down a high carbon material, it'll actually take nitrogen out of the soil because their bodies have a carbon to nitrogen ratio. But for all manures, it's really not an issue. So when we're calculating plant available nitrogen fractions, the plant available nitrogen is a combination of what's on the left here, the unstable organic nitrogen, the urea that's mineralized very quickly, stable organic nitrogen, which is broken down within the first year, and then on the right, the stable organic nitrogen, that's only going to be mineralized over years. So in the calculations, it's such a small fraction, we only calculate that if you use manure multiple years. In terms of loss of ammonia following a surface application of dairy manure, after 2 days, so again, this is on the y-axis, it's percent of ammonia lost, and on the x-axis, it's time in days. So after about 2 days, you've lost about 25%, and after 12 days, the longer that manure sits on the surface, the more ammonia you're going to lose. And for something like dairy manure, if you look at the average dairy manure, if you inject it, you keep 95% of that ammonia, so it's very beneficial, and you can lose most of the ammonia if it's surface applied. And because there's so much ammonia in dairy manure, you can actually lose about half of the plant available nitrogen. It goes from about 6 pounds per 1,000 gallons for surface application to 12. So you can double that plant available nitrogen if you inject it rather than surface applying due to this ammonia loss. And here's some of those coefficients. So manure ammonium availability coefficients. So as we go down from incorporating timing from injection, where you're getting it underneath the surface, and as we go down these rows, incorporation after 7 days or no incorporation, the percentage of that ammonia that you capture as plant available goes down. Along the top rows, you can see lagoon, liquid, and slurry. And sometimes people have asked me what the difference is. With lagoons, that's generally something in swine production where they have a large pit where all the manure is, and they don't stir it. Before they pump it out, they just pump the liquid off the surface. Whereas slurry is more what we get in most dairy systems in Virginia. They have a pit, but they will stir it very strongly before they land apply it, so it's got a much higher solid content than lagoon liquid. But again, if you inject it, you capture about 95% of your ammonia. Whereas in the bottom row, if you incorporate after 7 days or don't incorporate at all, for the slurry you only get about 25% of that ammonia. If you leave it on the surface, you lose a lot. If you inject it or incorporate quickly, you can capture quite a lot. And in the next presentation, I'll go through some of those calculations. For biosolids, it's similar application method, and there are 2 different columns. One's for biosolids with a pH below 10, and the other is biosolids with a pH greater than 10. So if you get it onto the surface, you'll capture 100% of that ammonia that's in that biosolids. And as you go down these rows, if you incorporate after 24 hours, 1 to 7 days, or after 7 days, it's the same concept. The longer that material stays on the soil surface, the more you're going to lose ammonia. If you get it incorporated quickly, you can capture that as plant available nitrogen. So organic nitrogen mineralization coefficients. So we have manure types here. We've got dairy, swine, and poultry. We've got spring applications. And then on the right, we've got winter top dress, spring residual. And you can see for dairy, it's 0.35. That means 35% of the organic nitrogen is going to be plant available. And if you look on the right, it still adds up to 0.35. It's just how much is going to be available in the winter top dress versus how much is going to be available in the spring. They just split it out between those growing seasons. And the dairy, it's only 35, whereas swine and poultry a lot higher. And again, that goes back to diet. For the dairy, they're fed forages or corn silage. The swine and poultry are corn and soybean meal, so their availability coefficients are much higher. So some organic nitrogen mineralization coefficients for biosolids. Again, it depends on how the biosolids treatment. Each wastewater treatment plant has a slightly different treatment system. Some are more common than others, but depending on the treatment system, you have different coefficients. These tend to be a lot lower than they are for poultry and swine, because in the sewage treatment plants, these are digested very heavily to try and kill microbes, but also to make the organic matter stable. And so they drive a lot of the nitrogen off to the atmosphere within the sewage treatment plant. And again, you've got what's going to be available this year compared to what's going to be available in future years of the very stable organic matter. So when you're trying to estimate plant available nitrogen, it's a sum of the total inorganic nitrogen you have in that manure minus what's volatilized to the atmosphere. You look at how much organic nitrogen is that manure, and you multiply it by the coefficient for the first year mineralization. And then you have residual if you're in a situation where you've been using manure for multiple years. And in the next presentation, I'll go through some of these calculations to make it a little clearer. And that is the end of the organic sources presentation. Any questions on that one before I go on to the calculations one?
None so far, but this plant available nitrogen calculations pretty important for the exam.
Okay, this is my final presentation, and I think my graduate student's going to do a Pre-Sidedress nitrate presentation. So we're going to, as we discussed in the last talk, we need to calculate the plant available nitrogen for any manure applications you're going to do. So this is a calculation sheet, and we're going to go through filling out the different boxes and look at where you get the different information from for the coefficients. So the first part is how much plant available nitrogen is going to be available this year. So you go out in the spring and you apply dairy manure, poultry manure. You can calculate how much plant available nitrogen is going to be available this year. And then the bottom part is what's going to be residual for next year. So the top part you would put in this year's nutrient management plan. The bottom part you would put in next year's nutrient management plan. So scenario one is for poultry litter. In this scenario, it's not going to be incorporated, so it's going to stay on the surface and lose ammonia. A spring application to forage, so that explains why it's not going to be incorporated. You don't till manure into a forage crop or you'll damage the forage. No previous litter application, and the forage nutrient needs is 120 pounds of nitrogen per acre. So you'll submit a soil sample to the soil testing lab. It'll tell you how much NP and K you need. And from that soil test report, you know you need 120 pounds of nitrogen per acre. And all of the poultry litter is going to supply all of the nitrogen. There's no other nitrogen source in this scenario. That's going to be important as we go through the calculation. So we look at we can look at the table of average manure analysis. This is table 8.4. I think it's on about, is it page 110 or so in the standards and criteria. I think in the 3-day school, Stephanie's going to give you a copy of the DCR nutrient management standards and criteria, so that this table's in there. But again, these are average values. You're going to need a specific analysis for what you're going to spread, because there is quite a lot of variability between manures and sources. So here we have analysis from Clemson. DCR pays for 1 or 2 samples per farm, and they pay for it to get analyzed at Clemson University Analytical Lab. Here at Virginia Tech, we do a soil analysis lab. We don't do manures. So when you look at it on the right here, those are the 2 numbers you need. ammonium nitrogen, and organic nitrogen. If you add them together, you get total nitrogen. But in this example, the lab has done the calculation for you. So total TKN, total nitrogen minus ammonium equals organic. So these are two numbers we're going to write on the form. So we're going to go to part 1 of the form. We're going to zoom in. We're going to write those two numbers from the analysis. Or first of all, in this scenario, we needed 120 pounds of total nitrogen or plant available nitrogen for the forage crop. And then from the manure analysis, it told us that we had 15.6 pounds of ammonium per ton and 62.69. So again, those numbers came from here, the 15.6 and the 62.69. That's where those numbers came from. That's from the manure analysis. So first of all, for the ammonia, we're going to go to the availability coefficient. It's in table 8-1 of DCR standards and criteria. So here's table 8-1. If you remember the scenario, it was going to be surface applied and left on the surface. So if you look at a dry litter for poultry litter, incorporated after 7 days or no incorporation, the coefficient is 0.5. So we write that coefficient of 0.5 in the calculation. And then we know, so we have 15.6 pounds of ammonium. About half of that is going to be plant available. That means we're going to get 7.8 pounds of plant available nitrogen per ton of the poultry litter. So then for the second part, the organic nitrogen, the 62.69, at the availability coefficient, we go to 8-2. So here's table 8-2 in your DCR standards and criteria. It's poultry litter applied in the spring from the scenario. So here we have poultry manure, spring applied, we have a coefficient of 0.6. So that means 60% of the organic manure, organic nitrogen is going to be plant available. So 62.69 pounds of organic nitrogen per ton multiplied by 0.6 comes out at 37.61 pounds of plant available nitrogen per ton from the organic fraction. We just add these together and it tells us for every ton, excuse me, I put a motion sensor light in my office, so if I sit still it turns the light off. But yeah, so 7.8 pounds per ton of plant available nitrogen from the ammonia, 37.61 from the organic, and we get 45.41 pounds of plant available nitrogen per ton. So then we move that down. We know we need 120 pounds of nitrogen to meet the grass needs. There's 45.41 per ton. So that means we need 2.64 tons of poultry litter to meet the nitrogen needs of the grass this year. So we take this organic fraction from the top part. This is from the manure analysis, and we write it in on the bottom part. And then in the top part, the calculation we just went through, we applied 2.64 tons per acre. So we transfer that down to the bottom part. So again, those are the two numbers from the top part that we transport or copy down onto the bottom part. We look at the analysis in table 3, and if you look at the scenario again, if you look at the line in green, no previous litter application. So this is the first time poultry litter has been applied, or at least the first time in the last 5 years. So again, we go to table 8-3, and we have 3 scenarios: rarely received manure in the past, frequent past applications, 2 to 3 out of the last 5 years. And as this is the first time it's received manure, the coefficient, you can see there on the right, 0. So obviously 62 times 0 is 0. We'll just finish it out. There's no plant available residual to next year, and it just comes out to 0. So because this is the first time poultry litter has been applied here, there's going to be 0 nitrogen residual next year. So the conclusions, this year you need 2.64 tons of poultry litter per acre to provide the 120 pounds of nitrogen that the grass needs, and there's no residual nitrogen that you need to enter in next year's nutrient management plan. Okay, we'll go through one more scenario. So scenario 2 is going to be for dairy manure. It's going to be applied before planting corn, which is very typical. That's where most dairy manure goes. On dairy farms, they mostly grow corn silage because that makes up the bulk of dairy diets. So most of the dairy manure in Virginia goes on to corn in the spring. It's going to be incorporated after 4 days, so that's obviously important for the ammonia capture. Manure applied to corn every year, so that's going to be important when we calculate residual. Previous application last year was 8,000 gallons per acre, and when we did last year's nutrient management plan, it said 18 pounds of residual from last year is going to be available this year. 27 pounds of nitrogen is going to be applied with starter. It's very common with corn, pretty universal to put some nitrogen out at planting. The corn seed obviously has no roots, so as it's trying to get canopy closure, it's very common to put a small amount of nitrogen out at planting to try and get that seed, get the roots down and get canopy closure to capture light and prevent weed problems. And 60 pounds of nitrogen is going to be broadcast with a herbicide. So we need to take this into consideration when we're doing total. And so in total, the corn needs 145 pounds per acre. So obviously 1 pound per bushel. The realistic yield expectation is 145 bushels per acre. So in total, the corn needs 145 pounds of nitrogen. We subtract the 18 pounds that's residual from last year's manure application. We subtract this 27 pounds of nitrogen from the starter and the 60 pounds of nitrogen per acre that was going to go out with a herbicide. That means only 40 pounds of nitrogen per acre is going to be needed from this dairy manure. So again, we go back to the same nitrogen calculations worksheet. And of course, first thing you need is a manure analysis. And the two numbers you're looking at is ammonium nitrogen in total. In the previous analysis, there was ammonium and organic. They'd done the calculation for you. They'd subtracted the ammonium from the total, but in this case, we're going to have to do the calculation ourselves. But remember those two numbers, 9.87 and 21.43. So from the scenario, we need 40 pounds of plant available nitrogen from this manure application. From the manure analysis, there's 21.43 total nitrogen per 1,000 gallons and 9.87 ammonium per 1,000 gallons. And we subtract one from the other, we end up with 11.56 pounds of organic nitrogen per 1,000 gallons. So just like in the previous example, we go to table 8-1 to work out how much of the ammonium is going to be plant available. If you remember from the scenario, it said it was going to be incorporated after 4 days. So that's this row, liquid manure slurry, and it's going to have 40% capture of that ammonia. So you're losing 60% of your ammonia with leaving your manure on the surface for 4 days. so we put that coefficient of 0.4 in there. 9.87 times coefficient of 0.4 comes out to 3.95. So you're getting, of this 9.87 pounds of ammonium per 1,000 gallons, you're only capturing about half of that, or 40% of that as plant available. So then for the organic nitrogen availability, we go to table 8-2. So table 8-2, we're dealing with dairy manure, which is the top row. It's going on in the spring. So dairy manure going on in the spring, organic nitrogen availability of 35%, 0.35. So we write the coefficient in the calculation table, and 11.56 times 0.35, you end up with just over 4 pounds of plant available nitrogen from the organic fraction. And you add these two numbers together, and it comes out at a nice round 8 pounds of plant available nitrogen per 1,000 gallons. So of the total 21 pounds of total nitrogen, you're only getting 8 as plant available. So again, we need 40 pounds from this manure application. There's 8 pounds of plant available nitrogen per 1,000 gallons. So 40 divided by 8 equals 5. So we need to apply 5,000 gallons in our nutrient management plan to meet the nitrogen requirements. Again, for the residual plant available nitrogen, we're going to take the organic fraction from the analysis from the top part. We're going to take the application rate of 5,000 gallons, and we're going to copy these two numbers from the top part to the bottom part of this form. So again, we're copying this from the top part of the form, the organic analysis from this year, and the application rate that we've calculated for this year. Then we need to look at the availability coefficients. So we go table 8-3, and if you look at the green line, manure has been applied to corn every year. So that's very important for residual. So table 8-3 residual factors, and it's going to be the bottom one. Continuously receive manure. So we can see the factor here that we're going to copy. So the availability coefficient is 0.2. So 11.56 times 0.2 comes out at 2.31 per unit. So 2.31 pounds is going to be residual per 1,000 gallons. We applied 5,000 gallons this year, so we multiply by 5, and we end up back up at 11.56. So in the top part, we calculated how much plant available nitrogen is available this year, and this is the residual that's going to be put in next year's nutrient management plan. Again, just the results of this dairy manure scenario. We calculated 5,000 gallons per acre needed this year to meet the 40 pounds of nitrogen per acre requirement. And then there's going to be 11.56 pounds of nitrogen per acre residual for next year, for next year's nutrient management plan. So the top part is this year's nutrient management plan. The bottom part is next year's nutrient management plan. And I think that's it for me. How are we doing on time? Are there any questions on that?
No questions. We are 6 minutes early, so pretty much holding right on schedule. For our last presentation of the day on PSNTs.
It looks like Catherine is on board, so
yes,
Katie,
she joined a while ago.
So Katie, if you want to start sharing your PSNT presentation, go ahead.
Yes.
And I'll remain on the line if anybody has any questions about any of the presentations.
Okay. Oh no. Sorry, I just exited my PowerPoint for no reason.
Technology, that's the reason.
It's just not as user-friendly as Zoom.
No. Especially if you don't have the app or using anything other than Microsoft.
Let's see.
Which share button are you using? There are two.
This window. Okay.
Aha.
Are you able to see this?
Yes, you just need to put it on presenter view.
Okay. Are you still able to see it?
Yeah, but we're still seeing it in the edit. Can you hit the play from start button? That might.
Okay.
Yep, there we go.
Awesome. Okay. Let me just make sure this is all right. Okay.
And just as a quick introduction, Katie is my PhD student, and she's writing up and should be finishing with her PhD here in a few months.
Congratulations.
Thank you. Well, maybe.
Oh, you've got it.
Okay, so I'm going to be going over the pre-Sidedress nitrate test for Dr. McGuire. First, we'll talk about what is PSNT. The PSNT is a soil test for nitrate. It's only used for corn, wheat, and barley in Virginia. And it has to be performed when the corn is about 12 inches tall and immediately before side dressing in organic nitrogen, or immediately before planting wheat or barley. And it can be used to decrease nitrogen recommendation if the soil has high nitrate. The PSNT is done at this specific timing because nitrogen moves fast in the soil. It's very mobile, and the concentrations can change very rapidly. So this test is taken and done with a very quick turnover time, and then use side dress immediately after you get the results and know how much to put on your crop. So these are the old PSNT nitrogen recommendations. As you can see here, for example, if a farmer did a PSNT and got a 22 parts per million, this is in parts per million, by the way, sorry, then he could cut back his side dress from his 100 pounds per acre applied to 25 pounds per acre applied. And these are the old recommendations from 1991. And the study was based on work at these sites. And as you can see, it's not all the regions in Virginia, and there are not too many sites with manure and sludge applications considered. So this graph right here we're looking at an example of corn yield response to nitrogen fertilizer at a low PSNT concentration of 6 milligrams per kilogram. Let me put my pointer on laser pointer so I can show you. The x-axis here shows the nitrogen rate in kilograms per hectare, and the y-axis shows the corn grain yield in megagrams per hectare. As we can see here, at low rates, the more PSNT fertilizer that's added, the more yield you get. However, when you get to this plateau, that's going to be your economic optimum nitrogen return rate. If you ever see it, it's going to be like EO and R. And that's the rate where your maximum return to nitrogen is reached. And it's the maximum amount of monetary return you can get because you're applying the most effective amount of fertilizer for the amount of yield you'll get back. So yeah, that's right there. And this has a higher economic nitrogen return rate compared to the cost of fertilizer, as opposed to this graph here shows us an example of yield response to nitrogen fertilizer at a high PSNT. It's at a concentration of 31 milligrams per kilogram. The x-axis shows us the nitrogen rate in, again, kilograms per hectare, and the y-axis shows corn grade yield in megagrams per hectare again. This here is showing us that if you apply high PSNT concentrations, you are getting less money back because although you're having a higher yield, you are also spending more money on fertilizer, which is pretty intrinsic to know, but sometimes might forget. This graph here, we're looking at relative yields versus nitrate concentrations determined by the lab. The x-axis is showing us the lab nitrate in milligrams per kilogram, and the y-axis is showing us the relative yield. Here it's saying that there's a decreased advantage in adding nitrate with a PS&T rate past the rate of 15 milligrams per kilogram or parts per million. This is the old standards. As we can see, it's saying that anything past adding adding nitrogen past 18 parts per million or milligrams per kilogram is basically ineffective because you're not going to have enough yield to cover the cost of fertilizer. Okay. So these are the old standards in a written out form. This is showing us the nitrogen recommendations for corn using PS&T in 1991. However, these are from 1991 and they need to be updated. There's been an increase in producers since of yield for producers since 1991, so there needs to be updates. We don't like this. So this is going to be a figure that's going to show us the corn yields and how they've increased from 1990 to 2017. Okay, the x-axis shows us the years starting with 1990 to 2017. The y-axis shows us the corn yields in bushels per acre. And now this is a fun question time. How much do y'all think yields have increased since 1991 in like bushels per acre? You can guess anything.
Any guesses, guys? Nothing will happen if you make a wrong guess. 50.
Ooh, okay, that's good.
25.
25? Oh. All right. So.
Oh, and then we had a 75. So 50, right on the nose.
Yeah. So since yields have increased by about 1.8 bushels per acre for 27 years, we get a 48.6 increase in bushels per acre since that 1991 recommendation. So right on the money, pretty much. Here we're looking at Virginia corn yields from 1990 to 2017. The x-axis shows the PS&T measured soil nitrate concentration in milligrams per kilogram, and this y-axis shows us the corresponding relative corn grain yield. Okay. Here we can see that the black squares and triangles represent the corn yields in 2014 and 2015. Compared to the black and white filled circles and diamonds from 1991 right here. Both of those studies for those recommendations looked at manure, biosolids, and cover crops compared to plots with no organic nitrogen input. Since in more recent years we've had higher yields, obviously, there's less nitrate available in the soil at the time for the PS&T. So what is recommended is that the recommendations be updated for nitrogen to make sure that all that extra corn we're growing actually gets all the nitrogen it needs. So this is the PS&T that's now approved for cover crop sites, and it's as of 2023. Here we have the x-axis with the PS&T soil nitrate concentrations in in parts per million, which is also milligrams per kilogram. And the y-axis here is relative corn grain yield in covered crop sites. The cutoff is now 15 to 26 parts per million in fields with cover crops rather than that initial 10 to 20 parts per million. With this new cutoff, there are some pretty good corn yields following the PS&T application in the cover crop fields. Yeah. This one right here is circled because it's an exception. That exception is circled because in that particular field, cover crop growth was wispy and poor, so that's why it affected the corn yield to a lesser extent than the legumes and the cover crops. So this is the revised recommendations. This shows us that the new nitrogen recommendations, when accounting for those increased yields, for example, if you have a nitrate concentration of 20 parts per million, you may want to reduce your sidedress by somewhere in between 20 to 50% because you already have a good amount of nitrate in your soil. You don't need to add too much extra. Okay. So this is the difference you can see for the old recommendation and the new recommendation. Okay, so for these studies, both of them used a linear plateau model where yield increased with nitrogen application up to a certain point, and then once it plateaued, that point was the maximum yield potential, and then the rest was if you add more fertilizer, what doesn't really matter because you're not getting more yield. So you can see here. In the 1991 study, there was no response in crops over 18 parts per million. So they added 2 parts per million where you could add that amount so that you have a little bit extra insurance, a little bit more nitrogen. For the 2019 recommendation, it included yields of crops over 200 with over 200 bushels per acre, and it cut off at 26 parts per million, but you don't have that extra insurance, that 2 parts per million like in the 1991. So whenever when you receive your PSNT report and everything, there are a couple things that you should remember. For an acre of soil, that top 6 inches of soil will weigh 200 pounds. So for routine soil tests, not the PSNT, you need to multiply the parts per million that you get back from them by 2 so that you can account for the fact that it's 2 millions of pounds in that acre as opposed to just, part per million. However, for PSNT, since we're waiting for those crops to be approximately 12 inches, their roots are going to also reach 12 inches. So you need to do about a 12-inch sample, and your parts per million will be increased or multiplied by 4 because instead of that 6 inches, you're going 12. So might ask yourself, where is PSNT recommended? Right now there is a 26 part per million cutoff for manure, biosolids, and legumes. So if you're wanting to get to there, it's the cutoff. So, but if you get somewhere between 15 to 26 parts per million back, you can cut back on the amount of nitrogen that you apply so that you don't add extra and increase your fertilizer costs without getting any yield back that will make up for the cost of fertilizer. So because of this, many different cover crop mixes will have a different C to N ratio. So it's good to get that tested. And there's also, every site will have a different history or adaptive management. So it's good to have this test to see and make sure that you don't over apply. So when determining nitrogen recommendations for wheat and barley using PSNT, there is no change when calculating. So if you're applying for wheat and barley, you're applying it right before you plant. So you don't need to go 12 inches down because the seeds are just in there. So you can do that 6 inches as if it's a routine soil test. And if the nitrate in the top 6 inches of the soil is under 30 parts per million, then you don't need to add any more nitrogen at planting because your plants already have enough. But if it's under 30 parts per million, then you can apply 15 to 30 pounds of nitrogen per acre. This is an example of a soil test kit. So there are some benefits and difficulties with the PSNT. For corn, it's only relevant if you're side dressing nitrogen, not if you're supplying all the nitrogen from pre-plant manure. So it's only during that around 12-inch growth, 12 inches above the soil. It's only around that stage that you do a PSNT. And it can save money on nitrogen fertilizer by decreasing nitrogen rate, but it can't increase nitrogen rate above the nutrient management plan. So you can't apply more than your plan allows. And sometimes it's very difficult to get soil samples to a depth of 12 inches if your soil's dry or if you're in a rocky area or something like that. And it's also a very narrow time window at a busy time of year to get that PSNT test turned in and then returned back to you. However, the main updates are that there was a cutoff. I'm so sorry. I'm not used to talking so much at once. So the original cutoff was 20 parts per million, where you would be recommended to do nitrogen application, but now it's being raised to 26 parts per million as of 2023, or sorry, as of 2019. And then there were some updates in 2023 as well for cover crops and corn side dress. That is, and I know I was pretty fast. Does anyone have any questions? I'll open up the chat too.
There's no questions in the chat.
Okay. Well, I'll just stay here until it wraps up.
All right. Well, that was the end of our agenda for today. Thank you all for joining us over the past 2 days. Thank you, Dr. McGuire. Thank you, Katie. If Paige, you're still on, thank you, especially for slogging through our technical hiccup. She was unfortunately the short straw on that side. Everyone, where would we find PSNT recommendations for cover crops? So like Dr. McGuire, Katie said, we're only doing these for grain or corn, small grains or corn, because you're looking at nitrogen applications and you really shouldn't be putting nutrients on cover crops. That's part of the cover crop thing. So this is really for wheat, for corn. Was the other one barley or rye? Barley. So those are the three that we're looking at PSNTs for. If anyone has any other questions that you think of at dinner, tomorrow, midnight, whatever, please send them over. I will happily get them to whoever could best serve answering that question. I've recorded this, so I will be sending it to DCR's IT to get it all compressed into a YouTube link, which I will send out to everybody, presenters included. I'll get some of the values presentations sent out from yesterday. If anyone's missing a flash drive, let me know. If you already let me know, I've got you down. That's all I have for today. Thanks everyone for participating. Hope you have a great rest of your day. See some of you all next week. And again, thank you to Virginia Tech for always giving excellent information. Have a great afternoon, everyone.
Bye.